Okay. Morning, Caden. Morning, everybody. 7 o'clock. Can you believe it? 7 o'clock on Monday. We got 5 people. Go 7 a.m. Love it. Happy to have you here. Warm up today. This is a little bit of a throwback to last week. When you notice something at Sling that's unsafe, that's a pretty broad category. What are some things you can do? What are some things you can do? Think about that for a second while I take the attendance. That's our warm up this morning.
You mind if I turn off the extractor?
I actually would prefer, thank you.
Isn't that?
It's too loud. Morning. Sophie. Jacob. Oh, Chris. Good. Great. All right, team. You notice something unsafe at Sling. What are some things you could do? Sophie, what's the thing you could do? Tell someone. Who would you tell?
The safety.
Okay. The SMS committee, Safety Management System Committee. How do you do that?
Discord.
Okay. This is actually the whole reason why I put this thing up there. Anybody know how you tell the Safety Management Committee about something you saw or something you did or something you noticed?
There's like the little channel in Discord where you can click and then it opens up a report.
All right, so let's clarify this because it's actually not in Discord. Safety management system is not in Discord. Safety management system, if you go to the hub and you go to student hub, you'll see this first button here is called pilot reporting system. Notice a safety hazard or had a flight event, report it here. So this is actually where you report it, but you'll notice that there's actually 3 different kinds of reports. So this is why I wanted to go over it. It's a little bit of like review / like a little deeper than some of the risk management stuff that we did last week, right? It's a little throwback. The first one is called the safety management system information, right? So this is for our folks to, when they notice something, you can actually make this report anonymously. And what happens is that the SNS committee, like this is like the whole point of our meetings. We go through every single report and we do the same exercise that we all did last week. What's the likelihood? What's the severity? What kind of mitigations do we need to do? Every single report. So that's everything from, hey, I noticed a lot of people are like walking across the ramp, head down on their phone, and I saw somebody almost get run over by a fuel truck yesterday. Like, no, they weren't paying attention, right? That could be something. All the way to, hey, somebody was lining up and waiting at Compton when we know that's against our safety policies and procedures. Anything like that, and you can submit them anonymously. The idea of doing it anonymously is then like, hopefully it encourages people to let us know when they see stuff so that we can do something about it. But that's how you submit that one. Then there's 2 other kinds of reports that I wanted to kind of bring to our attention. Flight crew report allows Sling to collect data from pilots about any event or occurrence in one of our aircraft. This report is only for internal use. It does not get sent out to any other parties. These reports are reviewed by flight ops and are a no-fault report, meaning unless you performed any intentionally unsafe actions, the Sling will not question or pursue anything against you, right? So this is something like, I was on a long solo cross country, right? And I was like chilling and doing my thing. I'm on my way home, and I'm like halfway home. I realized I never put the flaps up, and now I'm at 100 knots. So I've oversped the flaps, right? Shit, flaps up, right? Whatever. That would be a great reason to do a flight crew report, right? It's like, hey, I made a mistake. I own it. There might be something wrong with the airplane. Like somebody should look at the flaps now, right? Like something happened. but it's really important to know that like sling is you're not going to get reported to the FAA for that, right? Like unless you're doing something unsafe or like willfully being negligent. Sling just wants us to be able to say, hey, this happened, right? That's the flight crew report, internal. And then the last one is an occurrence report. This is what happens when Sling needs to have something to say to the FAA, right? So if you have an incident, for example, where you might need to report something to the NTSB, or you have an emergency and the FAA requests a report, Sling needs to have sort of the official statement of like what happened. So this is how we give Sling our official statement in an occurrence report. This one is mandatory when you have an aborted takeoff, declare an emergency, pan calls, or similar kinds of emergencies. Think of it as like if somebody from the NTSB or FAA is going to call Sling, we don't want Sling to be like, what happened? Right? Like, and they also need to know, like, okay, what's the official statement from us of what happened? So the occurrence report is our official statement to Sling, so that Sling can be prepared to tell whoever might ask and need to know. So obviously, if you do a flight crew report or an occurrence report, you can also do an SMS committee report, but the flight crew report and the occurrence report are not anonymous. Those you put your name. The Discord channel is for an immediate, I have had an emergency immediately and I need to alert all the important parties at Sling right now and get some assistance of what happened. So that's off-field landing, fire, you're stuck, you know, I'm trying to think of other examples of when it would be good to press that button. We might be able to think of some others, but that button, when you press it in Discord and you open a ticket that's like the emergency ticket, that pings like the CEOs, Jamie, all the flight ops, not me, thank goodness, that's above my pay grade, but it pings all the basically important maintenance, it pings a lot of people and gets their attention real fast, and then opens up a Discord channel for everybody to kind of have one conversation with you, right? So you can have one conversation with everybody in one spot instead of having to be like, hey, instructor, I had to do an off-field landing, and the instructor being like, what happened? And then the instructor tells Jamie, and Jamie's like, what happened? And then you have to explain it 8 million times. It's a way to get help quickly.
Is that like, would you press that button if, let's say, students was going on a cross country to Ramona? Plane overheats, they don't know what to do, and they're stuck there?
Not exactly, because that's like not something that in that case I would say call your instructor, right? Start with your instructor. That emergency button is really for I would consider it really there for things like, is this going on the news? Is this going on the news? Right? Like that kind of that's not really the perfect lens to look through. It's one of the lenses to look through. It's more, I would say it's more the urgency of how many eyes do you need on, right? If it's something like, hey, the engine oil was in the yellow. It didn't make it to the red, but it was in the yellow and it kind of stayed in the yellow. Start by, landing at Ramona, shutting down, calling your instructor, getting some assistance there first. Yeah.
Oh, where's that?
If the engine starts smoking and you have to do a diversion and now you're stuck somewhere, yeah, then you can open up that chat. Yeah. The emergency channel, Sophie, where did you find that in Discord? I thought it was there.
The currents.
Oh yeah, it's under information tab. So if you don't have the information tab expand information, and then it's called the occurrence reporting. And it says accident or serious incident. Accident or serious incident. So this is also like, I clipped another aircraft, or I don't know, accident or serious incident. These are actually terms that are defined in NTSB Part 830. What is an accident? What is a serious incident?
You guys probably went over, like, because when I started here, we used to, once we used to come back out of Echo and into Sling.
Yeah.
When we used to do the parking lot, we used to get away from the line and then get closer to the number so that we can park the plane easier.
Okay.
And then, when I started flying again, recently, they're like, "Oh, we can't do that no more."
Meaning you kind of spin around. You kind of come in and then put some power in and spin around so you can easily push back.
When we were here, we were just what I would do is we're on the line.
Yeah.
And I would just turn to the left to get closer to the parking spot.
Oh, okay.
And then turn off everything.
Oh, I see.
And then now we're oh no, you gotta leave it on the line, power it off there, and then, like
Drag it
yeah.
around. Yeah. That might have come from a safety management meeting and a mitigation from some kind of safety incident. I'm not sure. Yeah, sure. So just wanted you to know about all these. We are one of the very few flight schools that has an SMS process. I do think it's part of what makes us safer and right helps us reduce risk is having this process, which again can be anonymous. It can be small to big. If you have something that warrants like, hey, I screwed up, and it's going to be a no fault report as long as you weren't like, horsing around, then that's flight crew report. Especially if something needs to be looked at like in an airplane, like the example I gave, like, oh shit, I just oversped the flaps for a long time. That's something that will need to be looked at. Flight crew report. That's also something you'd want to tell your instructor right away, so they might be able to ground the plane for maintenance to take a look at beforehand. Again, folks, we all, everybody in this room has made mistakes while flying. Everybody has, and we all will again. None of us are perfect. The school understands that. The most important thing is that we create a culture here where we can just talk about it and own it up so that we can learn from it, first of all, because we learn a lot from our mistakes and from other people's mistakes, and so it doesn't happen again. And if we need to change something in our processes, we can do that. I'm telling you, it's chill. It's chill. As long as you're not being stupid, right? But otherwise, like honest mistakes, everybody understands that those happen. I have confessed to you multiple honest mistakes over the course of the last 7 weeks. So that is my way of demonstrating, like, they still hired me. I'm still here. We're fine. Cool. Thanks for that. Welcome to week 2. Now we're getting into some of the juicy IFR content. Week 2, today is nav sources, GPS, VOR specifically. Tomorrow is charts, specifically the low IFR chart. We're gonna have a really good time with the low IFR chart. Wednesday is departure procedures. And then Thursday is weather. Chris.
So on fourth flight, they gave us a Jepson's low chart, and I was like I accidentally clicked it on like on Friday.
Yeah.
And I'm like, what is it?
What is this sorcery?
It looks so
that changes view when you zoom in and zoom out. It is sorcery. So it's Jepson sorcery. I think it also looks weird. I have never been trained in the Jepson low and high charts, so we're going to be using FAA. I don't have slides for Jepson high and low. We will be using Jepson for approaches, and I do and departures, and I do strongly encourage us all to be using Jepson for those plates, arrivals, departures, and approaches. But for the en route charts, we're going to use FAA.
What about like you don't come up in like an interview for like the airlines?
I have never heard of that. I've only heard of them doing approach plates, departures, and arrivals. Yeah.
Road chart for Jepson is not simple. I was looking at it like
there is, right, just like there's a legend and a chart users guide for the FAA charts, there's also a Jepson users guide that is in our 4 flight. You press Jepson in documents, go to Jepson, it's all in there. I have not devoted the time to really learn it myself yet, and we don't have slides for it, so we're going to do FAA. And I also have never heard of a DPE. I'm not even sure all the DPEs know about it. So I think on your check rides, FAA IFR low will be the standard. Yeah. Friday is a holiday, so we will not be having a quiz this week. I am so sorry. No quiz this week. And it also means though no review, and weather is compressed into one day. I know we did a little bit last week, just to kind of get ahead of the game. We're going to see, and I've put in a request, I think that we should change the pacing a little bit. So I think we could easily spend 2 days on weather. So any weather we don't get to this week, we'll push into next week, and Kate and I will, Kate, who teaches the 11 o'clock, will coordinate on that. Any questions on the plan for the week? Yes.
Does airline use the Jefferson low and high charts?
It's a good question. I don't know. Somebody text their friend who works at an airline and find out. I don't know. I would assume probably yes, because the same reason that airlines use Jepson also applies to the high and low charts, in that there's no IFR low when I'm flying my SkyWest down to, Mexico. There's no IFR low, FAA IFR low when I fly my SkyWest up to Canada. Right. So it's too much to expect all the pilots to know every country's charts for every single place they fly to, especially when you get to the majors and you could be on United and going to 100 countries.
Yeah.
So they must. but I don't. Yeah, it's interesting. We've only had Jepson here at the school since January. So when I took this class last year, it was all FA all the time.
Oh, so you learned how to read the FA before reading the Jepson.
Yeah. And once you know one, you can go back and forth.
Yeah.
You can go back and forth. And also once you know one, you'll understand the joys of Jepson.
So it's not like the E6B calculator.
It's not like the E6B calculator.
It's like I started off with the like, I know what I'm going on. Let me try to learn this one first. I get to the electronic easy.
Yep.
And then to the electronic one, I can't use that.
I know, it's wild. Good morning, Paul. Welcome.
Hey, good morning.
All I know. Oh, there you are. Good. Okay. All right, team. Let's go ahead and get started. Which one of you just grab the door, please? So we're not disturbing anybody.
I'm cooking like this great.
Yeah, it actually is pretty good. I agree. Let's get this going here so folks can hopefully see the board a little bit. Drawn on the board today. All right, so the objective of today really is to focus on IFR navigation and navigation sources. We're going to talk first of all about GPS, then VOR. Those are our two primary ways of navigating in IFR. What are some other ways of navigating that we use in VFR? Just like a little private pilot review. Anybody want to yell one out?
Dead reckoning.
Dead reckoning. What's that, Chris?
That's when we do our space or like our place in the plane relative to what our nav log says.
Sure. I think you could say even a little more about that. You're not wrong. How do we do dead reckoning in VFR flight?
We calculate the true course based on the wind direction. So we fly whatever the heading
Yes.
we select for amount of time.
Yes.
And then, as Chris said, we compare.
Right? Exactly. Here's dead reckoning in this classroom. If I close my eyes and I take 7 steps that way, I should reach the door. Right? If I close my eyes and I take 3 steps that way, I should reach the chair. Like that's dead reckoning, right? It assumes that I know where the furniture is. It assumes there's no wind, or it assumes that I'm walking in a straight line. It assumes that my steps are even, right? There's a lot of assumptions of dead reckoning, but that's dead reckoning. What's another kind of navigation that we can use in VFR that we can't use in IFR? Pilotage. What's pilotage?
Using the VFR charts, like
Or just eyeballs.
Yeah, it's like our Mark II eyeballs. That's what I call it, right? It's like, look outside the damn plane. That's pilotage, right? Oh, look, Vincent Thomas Bridge. Oh, look, the refinery. Oh, look, an airport, right? Oh, which airport is it? Let's see. Well, I know the mountains are there. There's a freeway. Oh, here's the chart. Cool. That's Long Beach, right? Like that's how you do it. Pilotage, we cannot use, obviously, because we cannot see when we're in IMC. Dead reckoning, technically, we can still use in IMC. But we're not going to focus on that in this rating. We're going to focus on GPS and VOR because those are going to be our primary methods of navigating in IMC. We're going to do a deep dive on GPS, almost guaranteed to come up on your check ride. So a couple of just sort of like acronyms of things to start with. Anybody know what GPS stands for?
Global Positioning System. Global
Positioning System. Who's in charge of this system? What agency or government or country is in charge of this? USA, right? Oh, sorry, that's for Friday. USA, right? So specifically the Space Force, right? The new Space Force, they are in charge of the Global Positioning System. It is a US-based system. But this is sort of like Kleenex. This is a brand name for how we do something broader, which is GNSS. This is sort of the catch-all, and it stands for Global Navigation Satellite System, GNSS, right? So GPS is a kind of GNSS. So think of this as like it's an implementation of that done by the USA. There are other GNSS satellites constellations out there. Anybody know another one? This is not going to be covered in your check ride, but this is now just bonus information to impress your friends and family when you're at the 4th of July party on Friday. Or what other countries have them? Russia has one. China has one, I'm pretty sure. I think even India might have one. There's a few, right? The point is GPS, we use the term here to mean like, oh yeah, that's just what it is. But I just want to make it clear. GPS is an implementation of GNSS because you're going to see this phrase a lot, GNSS. That's sort of the catch-all term, whether you're using a US system or a different system, the concepts are the same. That's what that means. Yeah.
You said that our phones are able to pick up both, right?
The iPhone, if you look in the specs for your iPhone, it'll tell you which GNSS constellations it'll pick up. So I know for like, yeah, it'll tell you. I know, at least in the new iPhones, you're getting more than just GPS. Yeah. So that's just a little nomenclature I wanted us to be aware of. By the way, before we go further, what is my FAA source for all this? What publication can I read all about navigation systems?
AIM
Chapter 1, exactly. This is all AIM Chapter 1. AIM Chapter 1, AIM Chapter 5. These are our very hardcore AIM chapters for IFR. So those are the ones to like, I really don't know what to study today. Pick up AIM Chapter 1, pick up AIM Chapter 5. You'll always learn stuff from both of those. So also today, if you like are missing anything, you're like, oh, I want to go back. You have access to the slides. You also have access to AIM. Those would be my two sources I would strongly recommend. Cool. So how does this work? How does GNSS and specifically GPS, how does that work? So we've got a constellation of satellites that are constantly orbiting the Earth, right? They're going pretty fast. Oh, I'm doing that. This is how they're orbiting, right? They're orbiting around the Earth, and they're all in different alignment orbits. We have a picture. Here's the picture of it. Perfect. Thank you, slides. Okay. They're all orbiting the Earth at different inclinations, different paths, going like this. The orbits and the number of satellites are designed so that we can see at least 4 of them from any place on Earth at any time. Sometimes we can see more, but they're designed such that we can see at least 4 of them. Why 4? Well, let's first think about, I don't know, true crime shows. And they're trying to locate the criminal by their phone, doing like, their triangulation from their cell phone signal, right? How that works is you have like a, cell tower here, cell tower here, cell tower here. And each cell tower can tell you how far the signal of that phone is from the tower, but it doesn't know in what direction, right? It doesn't know in what direction. So this tower might say, all right, it's that far. And you can draw like a circle all the way around it. Like we know the phone is on that line. So that's also a lot to search. Maybe this tower tells you, oh, it's this far from me. This example is not working. There we go. And then this tower is telling you, oh, it's this far from me. And so we can triangulate using those 3 towers in a 2-dimensional way to know, all right, send somebody to search there. Where all 3 of those circles intersect, that's where we know the cell phone or the person is.
No.
Yeah, right? You didn't know this was going to be a 7 a.m. CSI class. Snitches, yeah. That's how it's called triangulation. Let me draw this better in the middle of the circle. Okay.
They're assuming the humans walking on the ground.
Yeah, this in order to only be able to use 3 cell towers to triangulate, it has to be a 2-dimensional situation, right?
Oh, so 3 gives you 2-dimensional.
Correct, right? This is why you need 3. If I only have 2, then they could be on either of these points, right? Or depending on which towers, these points or these points. To narrow it down to 1, I need 3 towers.
So
this is a 2-dimensional plane.
So in that case,
you see where this is going, right?
So if 3 gives you 2D, 4 gives you 3.
Correct. Because now imagine these not as circles, but as spheres, right? Coming out of the board. And now we need a 4th one to know, all right, where do all those spheres intersect? And that's why you need 4 GPS satellites in order to triangulate your position both laterally and vertically. You need 4 for your position. Yeah.
I think so far that's the best example of why we need 4 satellites in order to.
Oh, I'm so glad.
Yeah.
I'm so glad. Good. This is new. I didn't talk about this last round, so I'm glad to hear that. Yeah, good. Like I said, we're always getting better here at Sling, so that's working out. I'm glad. So you need 4 satellites to get your 3-dimensional position. Sound good, right? Cool. So in order for this to be the case, I think AIM says minimum of 24 satellites in the GPS constellation are constantly going around. I think we have actually more than 30. AIM will tell you exactly. And it's always constantly changing, right? There's more than 24 because we want to have some backups. Sometimes they break. We want to have some that are eventually going to get old. We're going to decommission them. We send up new ones. So we have somewhere more than, oh, here it says consists of 24 satellites, 6 different orbital planes. Cool. 4 satellites on each orbital plane. We actually have more than that. We have a few backups and other things that are happening. But you do need 4 in order to get that position.
I wonder how they go about it, swapping one out.
They send one up and then I guess they move them around. We have to have a guest speaker from the Space Force for that. Oh, actually though, who would absolutely know that question? Probably is Paul. Paul, who's our chief instructor. Okay, so there's Eric, right? Eric is the chief of instructors. He's my boss. He's the boss of all the instructors who he sat in last week. Yep. And then there's Paul. Paul is like the head chief instructor. So for all the paperwork for 141 and everything, he's the chief instructor. He oversees all the locations, right? He is the head of flight instruction for all of Sling. Yes, exactly. We're going to talk about WAS in a second. Paul's an incredible engineer, and he actually Wait, did he?
I think he did. That's what
I would not put it past him. I would not put it past him. Paul is fascinating. If you ever have a chance to sit down and talk with Paul, do not miss the opportunity. Yeah, he has he went to Caltech for become an engineer, and he's incredible. And he helped make the WAS satellites, is my understanding. We'll talk about WAS in a second. Yeah. So if anybody here knows, yeah. Paul's an impressive. I mean, there are a lot of impressive people in this hangar.
Your interview down to be I know the guy who made the boss.
Yeah, no, when you're in your interview to be a CFI here, and Paul's teach me the electrical system, and then I'm you're an incredibly accomplished electrical engineer, and now I need to tell you what an amp and a volt is. That's intimidating, but it works out. It works out, and he's actually super nice. Paul's not intimidating at all. He's super nice. Anyway, coming back to this, why was I saying this? Because we were talking your question about how do they ask Paul. This is the answer. I don't know. There's a lot of information here about the different segments of the GPS system. But the thing that I want to pause here on is so what are these satellites that are up there actually sending us? 3 things. And this is actually kind of important to know, right? The ID of the satellite. So I'm satellite 24 Bravo. I'm satellite 13 Charlie. I'm satellite whatever it is, R2D2, whatever the satellite's ID is. It's also sending out its position. And it's sending out some kind of time code. All 3 of these pieces of information are super important for us to calculate where we are, for the GPS receiver to calculate where it is in relationship to that satellite. Time code you see says atomic clock. The reason atomic clock is because the radio frequencies that are being sent out from these satellites travel at the speed of light. And so in order to accurately measure how far we are, I mean, we know how fast the speed of light moves, but we need to be very precise with our timing in order to track those very, very small amounts of time. ID, position, time code. That's what the GPS satellites are sending out to us. So with this information, the GPS receiver can begin to narrow down where we are. Just like if, in our example here from CSI and the criminal, right? When we have information all right, I'm this far, I know the position. I know how, the reason I know the position is because I can calculate how long it took for the signal to reach me. And I know how fast the speed of light is. So I can use that information to calculate exactly where I am. So 4 satellites for our 3-dimensional position. But there are a couple of potential problems in the system, some limitations, right? We're always talking about privileges and limitations, always, always, always. So let's talk about some of the limitations of the GPS system. Anybody have any ideas, especially those of you who've gone through the class before?
Like the GPS itself, or
Yeah.
when it's related to flight?
Oh, sure, both. But you know how we talk about like limitations well, we're going to talk about limitations of the VOR in a second.
Could it be side?
Sure, absolutely. Yeah, GPS is still a line of sight tech. Now in an airplane, it's usually not a problem because usually we have a very clear view of the sky from our airplane. And the signals, some of them, you know, like obviously I can still get a GPS position from my phone in this building. So I think some of them penetrate, but for the most part, it's still line of sight, right? If I go underwater, if I go in a tunnel, my GPS doesn't work anymore. Yeah. What's another potential problem or potential limitation that could happen to the GPS satellites?
Maybe
Sure, you want to say more about that?
they might be out of service, so we have like our plane will have to like do other get their information from different GPS.
Yeah, I'm just gonna put that they break. You know, they're just like VORs, right? Like
Little asterisks.
our poor Seal Beach VOR out of service, right? Same thing happened for GPS satellites. They break, they bust, they have problems. Yeah. A couple of other things just related to that, right? They can be off position, right? Maybe a piece of space junk bumps into it, so now it thinks it's in one spot, but it's actually in another. So it's telling me that it's in one position, but it's actually in another because the space junk bumped it and it moved.
So it kind of like the satellite doesn't realize the position move, so it's on like a fixed like plane.
We send it into a fixed plane. We send it into a fixed plane. And that's how it knows where it is, right? It's sort of like chicken and egg. Like the satellite can't use a GPS signal to know where it is because it
Yeah,
is a GPS signal.
like, bro, like your GPS signal should
But
be
we can observe from the ground and we can use physics and other things to know, okay, it's in this plane, it's staying there, this is how fast it's going. We can predict and know where it is. But sometimes maybe space junk, you know, gets it. Maybe the atomic clock is off, right? Atomic clocks are very, very precise, but like anything, maybe it's telling me the wrong time. That's possible. I put both of those in the category of break. Another one has to do with the atmosphere. So the atmosphere it's not a perfect vacuum, right?
Oh,
And we know how quickly the speed of light travels through a vacuum, but we live on Earth and there's a lot of molecules. We're going to talk a lot more about the atmosphere on Thursday, but just, you know, we talk about pressure when we talk about our gauges, all of those molecules refract light, refract energy, refract the signal, slow it down and change its speed. And because the atmosphere is not constant, the atmosphere is changing, it means that the speed we're receiving the signal, the speed of light, the speed of which the radio signal travels through the air, is slightly changing all the time. And when we're talking about such small amounts, right, like we're talking about milliseconds of time, those little changes could actually make a difference. Do they make a difference when I'm navigating on the 101 home? No. Do they make a difference when I'm trying to land an airplane on an exact spot on a 75-foot wide runway? Yes. Yes. So that's why in aviation specifically, we need to pay attention to all of these kinds of limitations. But how do we handle this? Well, we build in some features into some of our GPS receivers. One of these is called RAIN. Receiver, Autonomous Integrity Monitoring. Receiver, Autonomous Integrity Monitoring. We're going to come back to this. I just need where's my RAIN? Here's my RAIN. Receiver Autonomous Integrity Monitoring. And it does exactly what the name says. Receiver, so it's happening in my plane, in my receiver. Autonomous, meaning on its own without any intervention from me. Integrity monitoring, monitoring the integrity of the signal. It's monitoring some of these issues, particularly the break and the atmosphere. Well, not really the atmosphere. It's measuring, is it broken? How does it do that? It needs at least 5 satellites for RAIN. Why? That 5th satellite, that sort of extra satellite, that's the check satellite. So if we only have 4, we just have to trust it. We just have to trust it. But if we have 5, I can substitute in and calculate my position using 4 of the 5, right? And there are actually a bunch of combinations, maybe 16 combinations of that. Right? If I use like these 4 or these 4 or these 4, right? And so it calculates all that, and it can identify if there's a problem, if we have maybe something that doesn't add up. And when that happens, it'll give us an error, right? So this one says loss of GPS navigation. I don't actually think that's the error it would typically give us. It would give us an error called LOI, loss of integrity, right? Loss of integrity. And that's just telling you, you cannot depend on the signal right now. We don't know what's happening, but something is broken. Something is broken. So I think I'm sending you onto the runway at Long Beach. I might be sending you onto the Queen Mary. I don't know. Good luck. Rain. Now, even better, if we have 6 or more, now we can do fault detection and exclusion, right? So with 5, we only get, hey, the signal's working or it's not. With 6 or more, now we can actually narrow down which of those 6 might be not working. And we can automatically, the receiver will automatically ignore the one that doesn't make sense. So I've got 5 satellites that are all in agreement with each other. The 6th one is doing something crazy. I'm just going to ignore number 6. That's fault detection and exclusion. Or as I like to think about it, it's like rain, but now we're going to go one step further of saying, all right, I'm not even going to bother you. We don't even get a message on this. The GPS does this all automatically. It's just going to say, all right, we're gonna keep going. I'm going to ignore the faulty information. The more satellites you get, the more check satellites you have against each other. Example, GPS receiver is receiving signal from 10 satellites. One of those 10 is faulty. GPS without fault detection exclusion would give the pilot an integ message. So loss of integrity or integ. Those would be some of the error messages. And you would no longer be able to use it. However, if you have fault detection and exclusion, it'll just ignore the faulty satellite and continue on with our lives. Yeah.
So whether you have a detection or exclusion, it's still considered as a rain. Even if you only have detection, it's still rain.
You can't have FDE without rain, right? Rain is part of how we do fault detection and exclusion.
So
right?
To detect 6 and all combined.
Correct.
Okay.
We talk about it as if they're separate things. I think they're actually the same. They're related systems. It's just like my rain will not upgrade to fault detection and exclusion without 6 or more satellites. If I'm just on 5, it cannot exclude anything, right? It doesn't know which one to exclude. It just knows that something's not right. But if I have 6 or more and my device is equipped to do fault detection and exclusion, then it'll just carry on with our lives and we don't need to worry about it. So this handles this limitation, right? The broken limitation. It doesn't handle atmosphere. And this is where our next feature comes into play, which is called WAS. And just like I drew up here different nomenclature, I want to be clear on what some of the nomenclature is here. So we are, and this is what Paul helped him, implement in an event, right? Is something called a surface-based augmentation system. SBAS, surface-based augmentation system.
Is that the tissue?
Yeah, this is facial tissue. Now I'm going to tell you the Kleenex brand, which is WAS, Wide Area Augmentation System, which is a USA program. I was going to write FAA, but it should be operated by NOAA, the National Weather Service. I'm not 100%. AIM Chapter 1 will tell us, but I'll just put USA, right? So surface, just like we had sort of GNSS, and then we had GPS, which was the US implementation of the Global Navigation Satellite System. WAS, Wide Area Augmentation System, is the US implementation of surface-based augmentation system. We're going to come back to this. I just think this order that I'm telling you, it makes sense in my brain. Maybe it doesn't in yours, but it makes sense in mine. We're gonna sort of we're building the bookshelf now, and then we're gonna put some more books on. So WAS, how does it work? Well, in order to take care of this limitation, we need to measure things that are happening in the atmosphere. So the way we do that is we have, this is the Earth. We have a ground-based system here with a satellite dish on top. And we know exactly where on Earth that ground-based system is. We have charted it, we have surveyed it, we know exactly where it is. Then we send out 3 satellites. They get more and more bow tie-ish the more you draw them. And we send those not into the kind of orbits that we saw in the first slide with the GPS satellites moving. We send these into geostationary orbit. Geostationary, meaning unmoving as compared to the Earth. They actually are moving, but they're actually moving at the exact same rate as the Earth is turning. These are much farther out. The orbits have to be further out than the GPS constellation in order for them to be geostationary. They're moving at the same rate as the Earth is turning. So what that means is that relative to where I am on Earth, these 3 WASP satellites are always going to be in the same spot. So if I'm here in Torrance and I want to point to this WASP satellite, I always know it's going to be right there in the sky. Somewhere in the southern sky, because these operate in they're on I think equatorial orbits for the geostationary, right? So we're in northern hemisphere, so it's going to be yeah, that's south. Somewhere over there, right? Where exactly depends on where I am on Earth. But I know from here that WASP satellite. And so as the Earth turns, relative to me, that satellite stays in the same spot in the sky. It's always going to be right there. And we have like direct TV or like satellite TV. Same concept, right? Those satellite communications are in geostationary orbit. That's why you can mount a satellite dish on your house. It gets aligned. When the person comes to install it, it gets aligned once and it never moves. The satellite stays in the same place. Yeah.
There's only 3, right?
For WAS, yes. Moon, question?
Yeah. Just say there's only 3.
There's only 3.
Okay.
There's only for WAS. Now, this is only covered. Now, unlike GPS, WAS only covers a certain area. I think mostly North America, maybe Alaska, forget exactly. This is a name chapter 1. The answer to that's name chapter 1. But that's why WAS is an implementation of SBAS. If you go to other countries, other continents, other countries might operate their own surface-based augmentation system with the same concepts. And our receivers, some of the receivers can actually receive those, just like our iPhones can maybe receive some of the other GNSS implementations. But WAS is specifically run by the US government for North America. Yeah.
Yeah, so you just mentioned that WAS only covers certain area.
Yeah.
Yeah, so Justice.
Yeah.
He's from Hawaii.
Yeah.
He told me there's no WAS in Hawaii.
There's no WAS in Hawaii.
Yeah.
There's no WAS in Hawaii. That's correct. It's just too far from these 3 satellites, right? If you think about it, the 3 satellites can only, the Earth is actually curved. Is that controversial? Surprise, surprise. Right? The Earth is actually curved. So if there's a ground-based system over here or an airplane over here, they can't see these satellites over here.
Yeah.
That's how that works. Yes.
So I guess there's no APV approaches.
No LPV approaches or approaches with vertical guidance.
Yeah.
That's right. Exactly.
APV.
Not with GPS. Not with GPS.
What I don't understand is why is there like 2 satellites in California, like the ground uplink satellites, and there's like none in the middle of the United States.
Okay, so you're talking about these red and yellow dots on the screen?
Yeah, the ground uplink.
Yeah, so that's what these are, right? So we have various ground uplink stations or reference stations. We have a bunch of reference stations. Those are the yellow dots. The red ones are apparently the new ones. I don't know how old this image is. But you can think of the yellow and the red dots as we know exactly where they are on Earth. We've charted these exactly. And these are actually, what they're doing is they're not actually reading where the WASP satellite is. That's not really giving us that much information. What they're doing is they're reading the GPS satellites that go overhead. And they're comparing what their calculated position would be based on if they were only paying attention to the GPS signal and comparing that to where they know they are. So let me get a new color. Okay, we've got closer by, right? All these GPS satellites that are, you know, in their various orbits going around. So this is GPS, right? And this is the WAS. These ground stations are actually listening to the GPS satellites and comparing what the GPS satellites would say its calculated position is and comparing that to its known position. And then it can put on a correction factor, right? It can say, well, the GPS satellites say, if I was just paying attention to that, they'd say I'm right over here, right? 3 feet to the left, 3 feet to the east. So I'm going to say, well, then we should just correct the signals to say 3 feet to the east. 3 feet to the east. Now what it does is it transmits that information to master stations, and master stations do all that calculations across a wide area, figure out exactly what the correction factor should be, transmit that to uplink stations, and the uplink stations send that information to the WAS satellites, which then beam that down to our WAS receiver in our airplane.
Is there only one master station?
Looks like there are 2. I don't know exactly how accurate the map is, but it's probably accurate. The master station is where you're doing all the computations, right? So the ground reference station is really just, I don't even think it's that big. It's an antenna and a computer and an uplink to somewhere. And then where it's going is to the master station. Master station aggregates all those corrections, figures out a solution, sends it to the uplink station, which sends it to the WAS satellites, which then we can get the signal from the WAS satellites. So our plane is actually getting signal from the WAS satellites and the GPS satellites, right? Both. We need to have both in order for this system to work. So first, we're getting just our regular computed position from the GPS satellites. Cool, thanks. Now we're also, if we have a WAS-enabled GPS, we're also now getting the correction information from the WAS satellite. And I say the WAS satellite 1 because usually we can only see 1, maybe 2 from where we are in North America. We can actually cover all of the service area with 2, but then there's a bonus one and a backup. So we get that information, and then our WAS-enabled receiver applies those corrections in real time. Not only does it apply those corrections, but the WAS data can also say some information about this limitation, like blue is WAS. So it can also say, hey, ignore satellite 23 Bravo, ignore satellite this, add 4 seconds, add 4 milliseconds to the clock on this other satellite. So all the limitations here on break, the breaking limitation, also we can get corrected through WAS.
So it's constantly updating the mistakes.
Yes, and if you look in AIM chapter 1, it goes into deep detail about this. It says like, there's like slow corrections and fast corrections, and some of them are slow and they happen less frequently, and some of them are fast, they happen more frequently. All of that is happening. And then WASP also then compensates for this limitation of the atmosphere, which is constantly changing. All right, we've got more moisture, more humidity. It's taking longer for the signal to come to my plane. So therefore, I need to apply this correction factor. What all of this does, what is even the point of all this, is that it makes our GPS signal on our location far, far, far more accurate than without WAS. Our cell phones do not have WAS. It's fine to navigate on the freeway. But I need a more precise GPS signal if I'm going to put an airplane onto a particular spot on a particular runway. So, you look like you're brewing a question or comment. I don't know.
I'll let you finish.
The FAA allows us to fly around with GPSs for our en route phase, and for some even GPS approaches without WAS. And there are lots of airplanes out there that are IFR equipped. They have IFR equipped GPSs, IFR certified GPSs that don't have WAS. That's fine. But there are certain kinds of approaches that need such high precision in order to get you lower to the ground or to give you vertical guidance. We'll talk about this in week 4, different kinds of approaches that require this level of precision. For that, you need some kind of surface-based augmentation system. And in North America, we call that WAS, Wide Area Augmentation System.
Yes, you said it increased the accuracy,
Yeah,
WAS,
yes.
but wouldn't it more accurate to say an increased integrity?
Well, maybe. I think of integrity as just, can I trust the signal? You could have integrity without accuracy. You could have a trustworthy signal that's just not that accurate, right? Like, for example, if I'm going to a bar and I'm playing darts, don't do that. I'm not good. Yeah, I will poke you with the thing. But if I'm going to the bar and I'm playing a game of darts, right?
Yeah.
I could have integrity, meaning like, all right, I'm gonna throw this thing, and I know it's always gonna get sort of near the board. That's integrity, right? It's not. It's a thing. It's gonna stick on the wall. It's gonna stick on the board. Integrity. It doesn't necessarily mean I'm gonna hit a bullseye every time. That's GPS without WAS. Okay, cool. Like, I'm generally in this area, right? I'm throwing this dart. It's gonna generally be probably somewhere on the board. WAS is not only is it going to be on the board, it's going to be within that first inner circle or the next one every time.
Okay, so what you're telling me is, let's say our GPS is perfect. The integrity is perfect.
Great.
And the rain without WAS,
Yes.
the information that we're getting
Yes.
is less accurate than with WAS. Like
Correct.
the correct position,
Correct.
exact location is more precise.
Correct.
Okay.
Correct. Because, oops, sorry, computer. Rain is only correcting for breakage. Off position, atomic clock. Trying to think of other problems, right?
Mhm.
Rain is only correcting for, is it broken? It's not correcting for the atmosphere.
Right.
So all of that refraction that's happening with all the molecules in the atmosphere, that's what's introducing errors.
Right.
Because it's using ID, position, and time, right? So it's introducing a time error.
Okay.
Because the speed of light, which is how fast radio waves travel, right? The speed of light changes as it moves through different substances. And air, atmosphere is a substance, and the air, the atmosphere changes, it's constantly changing.
Mhm.
Also, we have things like maybe solar flares or other things that could change that signal for us.
What was the thing that
That's what WAS is correcting for.
Sierra actually brought it up, right? Like where like the signal goes through the atmosphere, but the atmosphere, because of the way it's bent and the way it is, it like actually moves it a little.
Literally.
Yeah.
Literally, I wish I would have brought the science experiment this morning, right? But if you get a glass of water, you take a laser, and you shine it in the glass of water, like it refracts, right? It moves, it bends the laser light. It's exactly what's happening all the time with all of our satellite signals through the atmosphere. In smaller ways. That would be an extreme demo.
Okay.
But it's the same concept of what's happening to the GPS signals that moves through the atmosphere. So this WAS is what's compensating. It compensates for break and for atmosphere. That's what makes it more accurate. Now look, rain is fine for most stuff. We're gonna just like be en route. If I want to get from one airport to another en route, totally fine. In that case, we don't need the level of precision. We don't care if the atmosphere today is bending at 0.2 milliseconds that way or 0.2 milliseconds this way. We don't care. Like, we're good enough. But if we want to use a signal to give us lateral guidance, vertical guidance, and get us really close to the ground, I need to know exactly where I am in order to feel safe and in order to be able to execute that approach safely. That's where you need WAS.
Oh, is there any GPS approach that you can do without WAS?
Yes, it's called LNAV, right? So if we look at the approaches,
Yeah.
and it's an LNAV approach, only lateral guidance.
Uh-huh.
You can do those with a regular FAA, just standard IFR approved GPS without WAS. But you do need, sorry for the folks who are new, but we'll get more into this in week 4. You need WAS in order to do an LPV approach, or / an approach with a vertical guidance, or an LNAV VNAV approach, which uses a baro-aided altimeter for your vertical guidance, but still gives you a localizer type, right? Like a localizer precision into the final approach course. But if you don't have that, you could still do GPS. You just have to do it to LNAV minimums, right? And that's a non-precision approach.
Right.
It does not have any vertical guidance.
Yes.
And it's going to have higher minimums, right? It's not going to get you as close to the ground. You just use LNAV. Yeah. So how do you know which kind of GPS you have? Well,
we look at the user manual for our Garmin 650.
Yeah, look in your what's all of a sudden got very zoomed in. You look in the usually when I press Control-0, it resets it. I don't know this browser. You look in your POH or your POH supplement or the user's manual for your GPS unit. Here's the slide I'm looking for. There are different technical standard orders that the FAA publishes that's sort of like a universal template for us to know what to expect in different kinds of equipment. The FAA issues technical standard orders for all kinds of stuff, including headsets, actually. If you ever notice, like if you go on like the Bose website or the Lightspeed website, you'll notice it'll say TSO'd or TSO compliant. Sometimes they'll advertise this. That means that they meet the standards of a particular TSO, technical standard order. This is sort of like the engineers of the FAA saying, in order for this to qualify as a, as a RAIN GPS, here are the standards it must meet. So they give them different numbers, and TSO C196 is an example of a TSO for a GPS receiver in an airplane. Where's the slide that tells me the different TSOs? I must have a slide for that. Are you serious right now? Is it in the cheat sheet you have there, the TSOs? The Pilots Cafe or the
I think so.
I think it is too. It should be in the
Technical
slides.
Standard order. So.
Yeah.
You want to take a look?
What does it say?
Let's go there.
Okay, this is what I need. Thank you.
No problem.
So it says, unaugmented older GPS that are capable of IFR flight but that cannot be used for alternate planning and are unable to perform approaches with vertical guidance require RAIN. So they must be supplemented with other forms of navigation. If you have WAS, it's going to be certified under TSO Charlie 145 or Charlie 146. So I'm going to put this in blue, right? TSO Charlie 145 or Charlie 146, right? Okay.
I'm using Pilots Cafe right now, so if you want to.
Oh, that's fine. Thank you. You hold on to it, and I will reference if I need to. Again, thank you for being on top of it here. So how do I know which one I have? I would look in my Garmin GTN and find out that our Garmin GTN 650 is certified. I'm pretty sure TSO 146, Charlie 146. Right? What's the difference between 145 and 146? I'd have to look that up. But I do know that in order for my GPS to do WAS approaches and to have WAS capability, that's one of the things I'm looking for. Charlie 145, Charlie 146. If I see another number like Charlie 196, okay, it's probably fine for normal IFR navigation. Not probably. It is fine for normal IFR navigation, but it's not going to do these extra corrections, and I'm not going to be able to get that level of precision that WAS provides for me. Yeah.
Just to come back for WAS.
Yeah.
The order, I mean, it happening constantly, but just to break down, the order of how it works is that all the GPS satellites send the information to the receiver, ground-based station, and they send it to the calculating station.
I would add a couple of twists there.
Yes, please.
The ground-based station is listening to the GPS satellites. Same way that your phone is right now to find its location. It's just listening. The ground-based station, though, unlike your phone, we know exactly where it is. So it can know, all right, well, it's telling me I'm over here, but I know I'm here. So there's got to be something wrong. That's all it's doing. And then it's sending that information to a processing center, aggregates that from a bunch of different ground listening stations, ground reference stations, they call them, to calculate some broad solutions. Like, okay, we know over here there must be something weird happening on the West Coast with the atmosphere. We need a different correction over there than we do in the Midwest, than we do in the South. It's doing all that math, crunching all those numbers. And then that central processing station then sends it to an uplink station, which is a satellite, which then sends that data up to the WASP satellites.
Oh, so it's sent to an uplink station that's goes to WASP.
The uplink station is literally just like a satellite dish, right? That is beaming that information up to the WASP satellites. Then WASP then beams that information back down to our receiver, our TSO 145 or 146 receiver. And then the receiver is also still listening to all the GPS satellites, right? WASP is not telling us any of our information about where we are. WASP is only telling us corrections.
Right.
So our receiver is still listening to GPS and calculating our position.
We're not getting our location from WASP.
We're not getting our
getting our location still from the regular.
Yes.
We're just getting errors.
Correct. The A here, right, in WASP and SBAS, augmentation, meaning it's augmenting it. It's adding something to make it better. It's not replacing it. It's not a surface-based replacement system. It's not a wide area replacement system. It's an augmentation system. It's making it more accurate by correcting for these two limitations.
But wouldn't, because GPS affected by the atmosphere, wouldn't WASP affected by atmosphere?
Yes.
That last signal.
Yes.
Yeah.
You mean this, where we're so, yes. However, the correction signals from WASP are not time sensitive. So all we need is the data. We're not measuring our distance from a WASP satellite.
Right.
So this limitation of the atmosphere when it comes to our WASP data is it's not an issue for us because we're not using the time distance, right, of that signal from the WASP satellites to calculate anything. We're just getting data. We're just getting correction data, like a set of corrections. Versus GPS satellite, we want to know exactly how long that signal takes to reach us, because that's how we know how far we are from that satellite. We know where the satellite is, because it told us. We know how long it took that signal to reach us. Then we can do a math velocity calculation, right, to figure out how far we are. But with WASP, we don't care how far we are from it. All we care is we get the data.
Right.
Then we apply that correction data to the GPS solution to make the GPS solution more accurate.
Okay. Interesting.
It's actually brilliant.
Yeah, it is very.
It's totally brilliant.
Is this something that like
No wonder Paul came out with it.
Correct, exactly. Only someone like Paul could have invented this. Yeah.
is this something that during our ground or the IFR we had to explain how it works?
So if you look in the ACS, which we will probably do week 5 as part of our review week, but you don't have to wait till week 5 to look, you'll notice that there is a task in there about navigation or what have you. And even if it doesn't come up on a check ride, it is almost guaranteed to be asked in your arcs and holds phase check. Was it asked in your, did Paul talk to you about? Oh, right, you did the improving control.
Yeah.
You've done arcs and holds.
Yeah.
I ask this every week, and I just always think you guys are already like basically on the cusp of your check ride. I just believe in you so much. It's almost guaranteed to come up because if you look at the both for 141 and 61, for you to be the second phase check, but for everybody else, the first phase check, it will talk about sources of navigation, and everybody's going to ask you about GPS because it's the most interesting and the most complicated and the hardest to conceptually understand. VOR, which we're going to spend 15 minutes on, we're going to spend an hour on GPS. So maybe they'll ask you about VOR, but VOR is a cinch compared to this, especially once you get into WASP, the calculations. Think of what we've talked about. We've talked about refraction through the atmosphere and geostationary orbits and There's a lot of interesting stuff happening here.
Standalone GPS is way more than the VOR station.
Correct.
Because
Well,
all of this is
yes.
without us even like knowing that it's
Correct. Well, and VOR really only gives us a one-dimensional
Mhm.
position. Doesn't even give us a two-dimensional position. Yeah. It just gives us, we know we're somewhere on this line. That's all VOR does. Yeah. So I would be prepared to basically explain everything we just talked about. And that's something to practice in a mentor session. Remember, 3 mentor sessions. It's something to practice in a mentor session. It's something to practice with each other. It's something to what there are some fantastic flight insight videos. You know, I'm obsessed with that guy, right? Like, he's got some amazing WAS and GPS videos. I think Kate might have even put some of the links on the chat. Maybe we'll refresh those to put them higher up on the chat now. But I know I'm pretty sure she put, if you scroll 5 weeks back, some great GPS WAS videos. Fantastic. But I would definitely be prepared to explain all this with great detail. If you roll into a check ride and the DP is like, tell me how GPS works, and you're like, well, there are a minimum of 24 satellites in a, in 6 orbital planes, but we actually operate more than 30 of them. After that, they're like, cool, like, let's move on. Not quite, right? They're still gonna want you to understand WAS, but this is how it makes sense in my brain. It might make sense in your brain slightly differently. The slides you can see are in a slightly different order. Explain it in a way that makes sense to you, but do be prepared to explain it. Yeah.
I have a question.
Go.
When you did IFR,
Yeah.
did you do this slide, the GPS navigation slide? It says link
Where does this come from?
Also, apparently Jimbo's class, because I got it from Justice. I'm assuming they will cover it. You guys didn't do it?
No. Somebody made this. It looks like a great presentation.
I think you said there was a flight insight video, but these 2 sources doesn't really break down.
No, it doesn't tell you exactly. It doesn't go into like AIM chapter 1 the way we've done.
Yeah.
It tells you how you use it, but it doesn't tell you how it works.
Yeah.
Yeah.
Because this, just this slide. This is what you meant by accuracy and
Correct. Exactly.
integrity. Yeah.
Exactly.
Yeah.
That's 100% it.
But I just couldn't. I don't think the slide explains it, but I couldn't find out why it was.
Yeah.
But yeah. Now I know.
Okay, good.
Yeah.
Are you all ready if I erase this?
Yeah.
Okay. There's one more thing we should talk about before we move on from GPS, which is how do we actually use it in the plane for navigation? So in our planes, we have an HSI, horizontal situation indicator, which includes a CDI, course deviation indicator, right? And in VOR, when we're navigating via VOR, we know that the CDI deflects based on how many degrees of radial, right? Like how many radials we are off or on course. So the distance from how far we are on or off course changes based on how close we are to the station, because the radials get closer together as we get closer to the station. So how does our CDI know how far to tell us if we're on or off course if there's no radials, right? In GPS, there's no radials. So the way that this works is basically we have to come up with an agreement about how much error we are gonna allow to be at full deflection. And this changes based on how far we are from the airports. I'm gonna draw an airway here. All right, and here's our center line of the airway. We need to know if the CDI is at full deflection, how far is that? And it's going to change based on how close we are to the airport. So when we're more than 30 miles from our takeoff or our landing airport, we're in what's called the en route phase of the GPS signal. And the width of, wow, that was really not. You know how I told you, maybe I haven't told you, like the pre-flight starts the minute you get on the ramp, because sometimes you notice stuff from farther away that's harder to see close up. Like close up, I didn't realize that my line was so crooked, and then when I stood back here, I was like, that's a crazy straight line. Same thing happens in your pre-flight. Okay, here's our en route segment. The dotted line is the middle of our airway. The distance that the GPS signal will tell us full deflection on our CDI is how much?
2 nautical miles?
2 nautical miles. So if I'm in the en route phase, meaning I'm more than 30 nautical miles from my takeoff, my departure, or my landing airport, it's going to be 2 nautical miles deflection. How do I know what phase I'm in? It's going to tell me up here in the status bar of my GTN 650. It's also going to tell me in the middle of my HSI. Now, when I'm getting a little closer, I need the signal to be a little more accurate, right? I need my navigation. I'm closer to the ground now. I need to be a little more accurate. Now we're going to be in terminal mode, which they abbreviate term. And then in this example, you can see right here, it says term on the bottom. Terminal mode, it gets twice as sensitive. So now full deflection is 1 nautical mile each side of center line. And this happens 30 nautical miles from airport, both your takeoff and arrival airport. Then as we get even closer and I'm shooting an approach, I need it to be even more precise. So now 0.3 or 0.3 nautical miles when I'm in approach mode. Oops. And I'll say APCH. So now full deflection is 0.3 of a mile. And that happens at the final approach fix for our approach. Week 4's approaches. But think of the final approach fix as like, we are really getting close to landing here. Now you'll notice that I drew these with like little like funnels. It's not like, oh, I'm now 30 nautical miles from the airport, so all of a sudden my CDI got twice as, like, you're not going to see it like jump and like get twice sensitive immediately. There's usually about, I think, approximately a 2 nautical mile kind of like funnel. So this will start about 32, like it'll start getting more sensitive about 32 nautical miles. This is matching flight site, right?
It says 31.
Greater than 31. Interesting.
Yeah, so it can be.
Interesting. So this is saying 2 and this is saying it's 1. Okay, great. So this is about 1 nautical mile. And this one is about 2 nautical miles from the final approach fix. That it's sort of like starting to get more sensitive. It's not an instant change. But you will notice that new annunciator on your GTN 650 or whatever GPS navigator you're using, and on your HSI for our G3X. It'll tell us what mode we're in. And why is that important? Because that's how far we are off. That's what full deflection means. We can no longer use radials or degrees. We're just using straight up miles. En route. We'll talk more about Victor Airways tomorrow when we go over the low IFR chart. Does anybody remember how wide a Victor Airway is?
4 nautical miles.
4 nautical miles to each side.
Yeah.
These suckers are huge, really. I mean, so, you know, even if I'm at full deflection and en route mode, I'm still within the protected area of the Victor Airway. Cool. Let's see if there's anything else extraordinary that we should discuss. It's doing that. Let's see.
And you said there's a flight insight video of the loss, kind of the breakdown you did.
Yes.
Okay.
Many good flight. I think he has at least 2. There's a problem. There
No
we go.
offense, I don't think the slides explain.
Here's the thing about the slides. And you could ask anybody here about this. This is not controversial. We're constantly trying to make the slides better. We all know that the slide. That's why I'm teaching it to you the way I'm teaching it to you. That's my job, right? If the slides were perfect, you could just read them and we wouldn't need a class. But we are making improvements. You're going to see improvements next week Week 4 is completely redone since the almost completely redone with approaches. It's all Jepson now. You're going to see new slides on Wednesday for ODPs. Now we have obstacle departures and since it's all Jepson now, that's different than last round. So we're constantly improving it. Oh, one other thing that we didn't mention, we'll talk about it more in approaches, but you can actually use a ground-based station at an airport to help improve the accuracy of GPS signals even more, to be able to do a precision approach using GPS signals from an airport. It's called GBAS, Ground-Based Augmentation System. And that would allow us to do a GLS, a ground-based augmentation landing system approach. There are not very many of them around the country. You do have to have an receiver that can handle this. We can't do that in a sling, but they do exist.
I don't think even LAX has GBAS.
I can't remember.
Yeah.
I think there might literally be a list in AIM Chapter 1. Like sometimes they do that. They're like, and here's a list of all the airports that have them. I can't remember.
I heard there are less than 10.
I think there are less than 10. I think that's about right. Yeah. It's very new. It's very fresh. Yeah. Cool. Shall we put GPS aside for a moment and talk a little bit about VORs? I'm like, VORs, decommissioning those. Well, here's another limitation, right, of GPS. They can be jammed pretty easily, right? Those satellites are far away. The signals are very, hard to hear. Obviously, we can because we have the receivers that use them, but it's actually not that hard to jam a GPS signal unintentionally by accident. This happened at Santa Monica a couple years ago. Everybody was losing their integrity on the final approach into Santa Monica. Santa Monica has no ILS and has only a VOR and then GPS approaches. The VOR is a circling approach and it's kind of, you have to go way out of your way. So everybody basically always shoots the GPS. So now GPS was basically out of service and the Space Force took it very seriously and they devoted a lot of resources to go find the source of the problem, which was somebody had been messing around with some radio equipment. They weren't even trying to jam it, right? But somehow they were sending out RF radio frequencies that were just jamming the GPS signal unintentionally. That happened. Yeah.
That'd be crazy, getting spotted by FBI.
No, by literally the Space Force. Yeah. Yep, exactly. I'm just trying to have a good time and talk on my ham radio. Meanwhile, jets cannot win. Cool. All right. So VOR is a ground-based system. It's telling us only information about where we are on a particular line from that station. We call it a radian. And it's measured, there are 360 of them, 1 per degree. So all I know from my VOR is I'm somewhere on this line. I'm somewhere on this line. That's it. I can also know if I'm going towards the station or away from the station on that line. So this is totally good to navigate from one VOR to another, or to navigate to a VOR or away from a VOR, but it's not good for much else. So that's why GPS is so helpful, because it allows us to now navigate outside of these VOR radios. How does this work? It uses 2 signals. The VOR sends out basically 2 signals that our receiver in our plane can receive. The first is a omnidirectional signal. I like to think of this as sort of like a strobe light that the VOR sends out. It sends out this strobe light, this omnidirectional signal, as a big flash. So wherever my plane is in relation to the VOR, I'm getting that signal. Then it sends out a sweeping signal, which only goes out on one radial, one of the 360 radials at a time, starting at 360 and going around. And it's timed. We know how long each radial blast is blasted for. So this is going to be an illustration. This is not what happens in real life, right? But say this gets blasted at, and we start a stopwatch. All right, well then we're going to have the sweeping signal, and it's going to start here at 1, then at 2, then at 3, then at 4, then at 5, then at 6, right until 90, 180, 270, and then back to the beginning. So we know which radio we're on based on the amount of time between the omnidirectional signal, the flash, the strobe light, and when we receive the sweeping signal, because that is constant. All the VORs do the sweeping signal at the same rate. So the longer the time between the omnidirectional signal and the sweeping signal, the further I am on the radio number. If I get omnidirectional signal and sweeping signal right next to each other, well, that means I'm probably 360, maybe 01, 001, 002, right? Like, but it's about time. That's how the VORs work. And it's doing this many times per second. Very, very quickly. That's how it works.
Not like sonar.
Except that with sonar, we're using time to like hear a reflection. In this case, we're using time to know which radio we're on. But similar concept in terms of we're using time to tell distance. In this, we're using time to tell which radio or our orientation or our bearing.
Because with sonar, like I'll send out the signal, and then because we're there, it'll like bounce back, and then oh, they're there. And then with this one, it just sends it out, and then it doesn't come back.
Right. It's not actually there's no bouncing that happens. We're just in our airplane over here, you know, on this radial. Airplanes. I think 7 weeks in, I get better. So it's hearing first this green signal, the flash, and then it knows, I don't know, 20 microseconds later, 20 milliseconds later, it now gets the sweeping signal. It knows that 20 milliseconds between the flash and the sweep calculates to the 060 rate. And so then my indications are going to show me that. That's right. Similar concept is GPS, right? GPS also uses time. We use time. We know how fast the signal travels. Satellite tells us where it is, so we know how far we are from it using that same concept of time to figure out location and distance. Good? Okay. VORs have a few limitations also. Let's talk about the limitations of VORs. Anybody want to say one?
Line of sight.
Yeah.
They're down.
Yeah, they can break. I actually heard Catalina yesterday. Catalina was working yesterday.
That's a shock.
It's not monitored. It is a shocker. We didn't listen to Seal Beach because it's still no temp. We didn't even bother. But they do break. What's another limitation of VOR? Cone of confusion. Say, what do you mean by that? Yeah. So based on how it works, what do you think is happening in the cone of confusion that causes that? Sophie, any ideas? Jacob, any ideas what might be, like if we use the same model of like the omnidirectional flash and then the sweeping signal, what's happening in the cone of confusion in our receiver?
You're probably picking up multiple of the time signals.
Yeah, exactly. Exactly. That's exactly what's happening.
You're picking up all of them.
You might picking up all of them. You might like at some point when you're right over it, you notice how the CDI just disappears. It's like bye. Like good luck. I don't know. That's too much for me. I'm out. That's exactly what happens. Your signal you start to pick up multiple sweeping signals. It gets way too sensitive. It gets confused. That's what's technically happening behind the scenes. Cone of confusion. Yeah. Any others, or those I think the main ones before we talk about DME?
Line of sight is like the.
Yeah, line of sight, right? And they also were sort of related to line of sight as they also have certain service volumes.
Oh yeah. Oh.
So
When they only reach out.
yeah, like they're only powerful enough. You can't hear, even if you have line of sight, you can't hear or tune in a VOR forever, right? They have limitations.
Oh, so is it like the ATIS?
Exactly. It's the same technology, right? In fact, the ATIS and the VORs operate on the same VHF technology. You think about almost the same, right? VORs operate typically, don't quote me, like about 108 megahertz to about what, 112, something like that. Again, AIM chapter 1 will tell us exactly. But if you think about like when you tune in a VOR, usually it's like around, I think, these frequencies like 108.2, 111.9, right?
Well, in that case, wouldn't it be 113, like 113? Because it's in LAX, like 113.
Oh yeah, maybe it's 113.
Still reaches 105.
Okay. Okay, we're gonna erase this.
I
The
mean,
point being, there's like a lower level, like a lower number of these frequencies.
To 117.
Thank you. Okay, so I had the 108 right. What was it? 117.9 or 5? All right. Is that in chapter 1? Sweet. Jacob's on it. Great. All right. So that's the frequencies. And then what starts at 118.0?
ATIS?
VHF voice. VHF voice, right? ATIS, ground, tower, approach, all the way up to what? 133.9 or 5, something like that. I think. I don't know. That's also in chapter 1. But we're gonna put a question mark. Don't quote me. Okay. But it's the same exact technology. So exactly right. In the same way that I can't hear the ATIS from far away, I can't hear the CL Beach VOR from far away because it just only has a certain amount of power. So we call that the service volume, and different VORs have different service volumes. Why is this important to us? When we're planning an IFR trip, we need to make sure that if we're going to navigate using VORs, that we always are able to hear or tune in the VOR. Now, tomorrow when we talk about the IFR load chart, the IFR load chart takes a lot of that guesswork out of the equation for us by telling us how high and how far we need to be in order to get a reception from a VOR receiver. But if we're going like off route, then we need to be able to interpret these service volumes. And the FAA has two kinds of service volumes for VORs. The old version and the new version. These are all in AIM chapter 1. In fact, this image is literally clipped from AIM chapter 1. And it'll tell you, it almost looks like a wedding cake. See how it looks like kind of a wedding cake where like lower down, it doesn't have as big of a service volume as higher up. So here we're looking at the new VOR low, which is a code VL. So starting at 1,000 feet, between 1,000 feet and 5,000 feet, that's where this first layer is. You should be able to tune in the VOR within 40 nautical miles. It's a radius, 40 nautical mile radius. But once you get above 5,000, 5,000, 18,000, if you're on a VOR that has a service volume of VL, new VOR low, you should be able to actually tune in that VOR for 70 nautical mile radius. And then this one is like, it almost looks like a Bravo airspace, right? With like different layers and.
So, with service volumes, say it's one of them is like sea level to the ground.
Yeah.
Like here.
Yeah.
So we can only go up a certain height up until we lose signal. But if it's above us, does that mean we can only go a certain amount of descent before we lose it? Or
Yeah.
do we have like signal all the way down?
No. So for example, say you're on this VOR low, the new VOR low service volume, right? With VL is the code. And I'm flying along here and I'm at like 6,000 and I'm 65 miles away. All right, well, that's in the service volume, right? I'm between 5,000 and 18,000. That's this chunk here. And I'm at 6,000 and I'm 65 nautical miles away. That's like right here. Cool. Sling 805 of Zulu, descend maintain 4,000. Descend maintain 4,000. 805 of Zulu. Now all of a sudden I'm here.
Oh, you're not gonna get it because
Correct.
it's okay.
Correct. Correct. Now these are drawn with very sharp angles. That's not how radio waves work, right? Like actually this is much more curved and maybe you'll actually be able to hear it 75 miles or 80 miles or what have you. But these are drawn in this way. This is what you can be sure you're going to hear. This is where you can, for your planning purposes, you can rely on this service volume. You'll notice at the bottom, like here below 1,000, see how it's kind of like shaped like a little inverted dome? And that's same reason, line of sight, right? Like yesterday I flew out of Santa Monica. We needed to do a VOR test, this particular plane. Actually we need to talk about VOR tests. Good, we still have time for that. The VOR needed to be tested. Well, good news. There's a VOR at Santa Monica Airport. However, for some reason, where we were on the field, the VOR receiver could not tune in the signal. It just couldn't hear it. Why? Well, it's because the service, this is a curved service volume here at the bottom, and I guess we were just in a particular place. Maybe we're blocked by a building or something else. Or maybe the plane's receiver is in a different, whatever reason we couldn't hear it.
So now with this, now we had to get personal minimums with VOR. So if our distance is, what is it, 70 statute miles on top?
Yeah, right here. This one is
So
70
would that-
miles. Yeah, 70
Okay.
nautical miles.
70 nautical miles. Would that mean that we want to choose one that were like 65 nautical miles?
I
That
never-
wouldn't be in range?
Look, y'all can have personal minimums for whatever you want, and you should. And to be honest, Chris, I love that you're thinking this way, because I say this a bazillion times, I'll say it again. Risk management is on every task of the ACS. Risk management is on every task of the ACS. So the fact that you're thinking that way is exactly how you should be thinking as a competent pilot, especially a competent IFR pilot. That said, I've never heard of people having personal minimums for VOR service volumes. I think these are already pretty conservative.
Oh, so they already have.
I think they've
Even
built
though-
in. I think they've built in a pretty good margin of error. So you could, if you're doing off route navigation, off of airways, and you want to make sure you can tune everything in, yeah, you could do that. However, I also think that use case is now becoming more and more of an edge case, right? Typically, when we're navigating off route, we're either on vectors from ATC or we're on GPS navigation. Typically, this is important to know for your knowledge. It's important to know for how the FAA determines where or when you can receive VOR signals. It's how they design the map. Oh, we had another person join. Who else joined? Oh, Wayne's here. Welcome, Wayne. Sorry, I just noticed you were here. So it's important to know all that, but and in your actual cross-country planning, I have never had to look up a VOR service volume because I'm just staying on an airway. And part of the beauty of VOR, of the airway system, the federal airway system, is that the FAA has done this calculation for us and told us that if we're on the airway at a certain altitude, we're guaranteed signal coverage.
Oh, that's where the MOC comes in.
And the MEA. We'll talk more about that tomorrow. But yes, exactly. So in your day-to-day IFR life, you should know about this. It's important background information, just like you should know how WAS works, important background information, especially because if something goes wrong, that's how you troubleshoot, right? The more you know about systems, the more you know about how stuff works, the better troubleshooter you are in an emergency. And day-to-day, just know it's a name check or what. I know some people memorize these for their check rides. I never found that necessary. This is like a VOR service volume. Like I knew what it was. I could explain it the same way, but I did not have this memorized. This picture was not memorized. I knew where to find it in name chapter 1. The DP asked me about it. I knew where to look it up. Is the DP going to be upset about that? How could they possibly be upset about that? This is not something I need to have memorized in the air. This is a pre-flight planning piece, and I know where to look it up. That is within standards of the ACS. Part of this, there's so much an instrument, right? I also am trying to tell you like where to spend your energy and where not to. So like know how it works, know about the service volumes, know the difference between the old and the new, what the codes are, but don't, in my opinion, you do not need to waste brain cells memorizing this. Just know where it is.
Have you ever been into VOR?
No. Have you?
I have, yeah.
What was it like?
What do you mean by that?
Like
the building?
yeah.
Oh,
in the VOR, you see the doors? Yeah.
Oh, yeah. What?
How
Yeah.
did you arrange that?
I went to high school in Minnesota.
What?
Yeah, and one of my science teachers.
Minnetonka?
Not in Minnetonka, but it was. I can actually find the city.
Nice.
Over there, but
I just picked a random Minnesota city.
yeah.
Here.
But yeah, my science teacher, he had a private pilot license,
No way.
and he arranged like a temporary aeronautics course,
Yeah.
and we had a local airport that had a VOR. And we like made an appointment and we went in there. Just a bunch of computers and
What?
That's cool.
That is so cool.
There's no one in there like.
No, they're unstaffed.
yeah.
They're monitored, and actually AIM Chapter 1 has a lot of information about how they're monitored. And actually the NOTAM for Catalina right now, it says not monitored is basically the NOTAM. Because in order for them to be reliable, they do need to be checked. And so there are 4 different categories of how they're monitored. I did a deep dive in this part of AIM Chapter 1 last week for reasons that I will not go into now. But that is awesome. That is awesome. I'm into it. And if I had my life to do again, I would be that teacher doing temporary. That's not true. I love my life. I would not do it differently. But that's awesome that you had that.
There's a reason why
That's correct. That's correct. Things worked out this way. Okay, there are a bunch of slides here that will help you with the written. And in particular, reverse sensing is also one of the limitations. We missed that one.
I think we don't have to worry about reverse. Oh wait, but
First, let's start with what reverse sensing is. What's reverse sensing?
Kind of literally what it says. When it's
Yeah.
fast, we have to go to the left, you actually go ahead.
Go to the
If we have tuned to a reciprocal radial, the CDI is going to indicate backwards indication. So usually we drive towards the needle, but if it's reverse sensing, we have to pull the needle.
So would that mean if we're on the radio 0, but we're tracking 180, would it make us go to the right to go left?
Yes. Or in the example on the board, let's call that the 060 radial.
Mm.
Quite the 060 radial, but let's call it the 060 radial. And the little airplane is going to the west, right? Or so we'd have a 2 flag on our display. What if we're going to the station, what radial should we actually have programmed in?
There was
Which is what from 060?
2.
Say it again.
Is it the 240?
240, the +2 -2 trick.
Yeah.
I'm saying that because literally I learned that in this class last November. Nobody had ever taught me. I'm like trying to do like complicated math in my head. And so yeah, so here's how this works on reciprocals. So say I'm on the 060 and I need to find the reciprocal of it. I start with the first digit and I either do a plus or -2 to it. Can I do a -2 to a 0? No. So I'm going to do a +2 to get to 2. Then I'm going to do a +2 -2 again on the second digit. But if I did a plus on the first one, I'm going to do a minus on the second one. If I did a minus on the first one, I'm going to do a plus on the second one. So since I did +2 here to the first digit, I'm going to do -2 here. So that's how I quickly get 240. Oh my God, it was, I was like, how are all these people doing -180 in their head so fast? Literally, I'm in this class. And then they're like the +2 minus, nobody had ever taught me that until last November. I was like, revolutionary. There are a couple of times where it doesn't work quite right.
360.
What was it?
I think it's 360 or like 270. It gives you like a weird number.
270 should work. I think it's more like 190, right? So this should be, if it should be +2, right? So that would be 3, but then -2, that should be 7, right? So that didn't work right.
Yeah, so I get to
Like the ones.
It's so it actually should be right to
010.
yeah. But the way you do it is radios from 0 to 180, you add 2, and then from 180 through like 360, you like subtract 2.
right. Yeah, it's whatever. Basically, you know that this first digit has to be a 0, 1, or a 2. So it's whatever math will get it to that right. Yeah, so there's a couple of examples like that.
It's like-
Right? But most of them works instantly.
Like 1 or 2
How-
that give you.
What's that?
Goodbye using my fingers.
Yeah, exactly. I'm telling you, it's terrible. However, that said, when you are under the hood and it's been a long lesson or a long check ride and you're trying to figure out a reciprocal, just take an extra breath and double check, because for some reason I made mistakes on this more than I'd like to admit. It's like, how can I make mistakes adding 2 and subtracting 2? But
Awesome.
there's a lot of brain waves that happen in IFR flying, especially when it's new. So just take a deep breath and be like, is that the reciprocal? Cool. We have tools in the airplane to help us verify, right? So the CDI needle, if I have this set to 291, what should the tail be pointing to?
29.
But if this is heading this is set to 291, which the tail of this be set to. It's actually
Should be 1-1. Yeah.
oh yeah, this is one where it doesn't work, huh? What is an example? 111?
Oh,
111.
Was it 291?
Yeah,
Oh, okay. 111.
111. Yeah. Okay, so but so down here it should be like, oh yeah, it's about 111. Yeah, that looks right. Cool, verified.
But I think most of the numbers
Yeah.
that you can do, I mean, at least for me,
Yeah.
you can do with the head.
Yes.
It's you can do it, but
Yes.
some like 270, like oh what was it? And when it's complicated, then you can do +1 minus or +2 minus 2. So when it's 291,
Yeah.
wouldn't it be easier to just subtract it instead of thinking about it? Because 180 is smaller.
Maybe.
Like all the yeah.
Maybe. This is the kind of stuff where, also in IFR flying, there's a lot of ways to do it. Hold entries all of week. Next week is going to be holds. It's the same thing on holds. There's like, we're going to give you a menu of here's like 3 to 8 ways of doing it. Pick the one that tastes good. You should probably try them all out, right? Like don't be the picky toddler who doesn't eat anything except string cheese. But, we're all going to have our preferences and our ways of doing it. If it works out, it works out. My parents were like, this is what's for dinner, eat it or you're not getting food. I had to eat stuff. Yeah, it works. You can literally get out and do -180 +180. Like you can literally, that is a lot. I'll tell you, when I was doing my Arsenal space check, I literally drew every hold on my knee board. I just drew it out. It worked. It worked.
Could you just you don't gotta show the DP here map, right? Can you just like, oh, there was a reciprocal like 0, just like twist it until like it lines up?
Whatever works, as long as it's not unsafe. As long as it's not unsafe. If they're seeing you do that every time, they're gonna probably wonder. But
they're like, oh, what's your like reasoning behind it?
Or look, just say it out loud. You could say something like, "Wow, my brain's really fried. I'm just gonna spin the CDI to verify my math." Not only is that allowed, that's demonstrating risk management in every task of the ACS. I know I'm fatigued. That is a risk. That's a hazard. I'm doing something to mitigate that risk. That's single pilot resource management. That's on the ACS. Just by saying that out loud and explaining it, why you're doing it. Now you went from question mark to gold standard.
Yeah. And actually, this is what my instructor taught me.
Yeah.
That way I think that's pretty accurate because assuming that your heading is straight.
Yeah.
Because the first digit is not going to change.
Correct.
So if it's 291,
yeah,
you go about 180.
Yeah.
And put the first digit at 1.
Okay.
And when it's 121, it's probably 2 off to the left. When it's 101, it's probably off to the right. So 111 is it should be right because it's 180, not does that make sense?
No, but it might to others. It doesn't, right? Like this is the beauty of it. Like it makes sense to you, and this might be what unlocks it for Sophie or for Chris or for Wayne or somebody else, right? Like it's the conceptual understanding of these things. Like is we can get to the same answer with different sort of pathways that make sense. I'm glad you shared it. Glad you shared it.
That happened to me with Taylor.
Taylor
was teaching the class.
Sorry, it's contagious now.
And then for the longest, I couldn't figure out what kind of hold entry I was doing. I was like, yes, if like my instructor would never give me a direct, so I knew I wasn't direct. Teardrop? Oh, okay, it's parallel. And then he told just get your pencil, and then if your heading is on the right, but your pencil is up on the left, then that means that the parallel, because the heading is supposed to be your teardrop entry.
Next week
with holds,
next week with holds, we're gonna spend a lot of time everybody telling us the way they do it.
Their method.
Because the way it works for one person, it will not work for another, and then it might work for the third. So there's a lot of ways to do it. Holds are extraordinarily conceptual. simple once you understand the concepts, but getting there is hard, especially flying them, right? Doing them on the written is one thing. Flying them in the airplane is another thing. There are slides in here for the written about something called the VOR trick. I recommend you read those when you're preparing for the written, or even better, Shepherd has a whole video about those questions. Just watch the Shepherd video. It's like 17 minutes. It's an investment. But after that, I was like, I aced all the VOR questions on the check ride, or on the not the check ride, the written. Yeah. Let's talk about some inspections. Okay. The GPS, because of its TSO, does not need to be inspected. Right? It's automatically like there's, especially WAS, right? Like we're getting the corrections off of WAS. However, our VOR receiver needs to be inspected. What's the acronym for our inspections? Aviate or AAV8, right? So the V in that is VOR, right? I think it's wow, do I have this one memorized? Let's see. 91-171?
Oh, there's a firing?
Oh yeah.
I think it's right.
Is that right? Hell yeah.
171.
Oh, it feels good. This is why you know I'm a nerd. Party tricks that no one cares about.
No, if you go to the lounge, and there's a bunch of pilots. Oh, no way, you know that.
Yeah, or they're gonna be like, somebody's got too much time on his hands. Like what? I teach the IFR ground. Leave me alone. Here's the actual citation, right? No person may operate under IFR using VOR unless you've done the following. It's maintained, checked, or inspected, and has been checked in the last 30 days, which is a different amount of time than a calendar month. Let's just be precise. This is 30 days. Let me tell you something. Next time you go out to one of these sling planes, see when the last time the VOR was checked. Where would it be? You know? There's a paper log in the binder. That's where we keep it.
Because technically speaking, you can put it anywhere you want.
Yeah, you could write it on a post-it note, and that counts as long as you have the right information per 91-171. But we keep it here in the sheet on the binder. Legally, in order to use VOR, to do anything on green needles, you have to have had the VOR tested within the last 30 days. Good news, unlike other tests like pedostatic and annuals, any private pilot or better can do the VOR check. Not a student pilot. The private pilot or better can do the VOR check. Actually, the very first time I signed my name, Neil Spears CFI, was on a VOR check. So if you ever find that plane where it says Neil Spears CFI, you can just feel warm fuzzies about, it's the first time I signed my name CFI. Here's how you do it. There are a bunch of different ways. Some airports have an FAA operated test signal. This is called a VOT. Slides. The VOT. This is basically a signal that's constantly sending out 360 from 1802, no matter where you are. So it's sending out the sinking signal, and then it's sending out the sweeping signal, but instead of it being sweeping, it's also a pulse at exactly the right time. So no matter where you are, you should always be at 360 from or 1802. So you tune in the VOT, which you find the frequency in the chart supplement. And then it needs to be either 360 from or 1802. And then the amount of tolerance you're allowed is plus or minus 4 degrees. So you sink it, you center the needle, and you read what it's showing. If you're 360 from, it can be all the way, 356 to 004. Any of that is within tolerance. That's the VOT check. You can also use a surface designated VOR checkpoint. In the chart supplement, you'll find a list of the surface-based checkpoints. It'll tell you exactly where to be on the airport, what VOR to tune in, and what radial to set for your test. There aren't that many of them. Van Nuys has a ground checkpoint. I think Long Beach has a ground checkpoint. Don't quote me on that. It's in the chart supplement. Same amount of tolerance, plus or minus 4 degrees in order to pass. Now, if you don't have any of that, then you can do an airborne checkpoint. And so in the chart supplement, there's also airborne checkpoints. Airborne checkpoints, however, give us a little more tolerance, plus or minus 6 degrees. It's because we're in the air. We're not exactly sure if we're exactly over the right spot. Like maybe it was 10 seconds ago, maybe it was 10 seconds from now. So they give us a little more leeway. Airborne checks, plus or minus 6 degrees. And if no check signal is available, select a VOR radial that lies along an airway, select a prominent ground point along the radial, and note whether or not it's correct. And that's also a tolerance of 6 degrees. It's going to make a little more sense when we look at the IFR load tomorrow. One of you please remind me. I'll try to remember too. I'll demonstrate this in the IFR load chart tomorrow. But the bottom line is airborne checkpoints plus or minus 6 degrees. All the others plus or minus 4. If you are lucky enough to have 2 VORs in your plane, you can check them against each other.
That's bougie.
Oh, that's not only bougie, but actually most of the Cessnas I've flown, the 6-packs that are way less bougie than our plane, most of them have 2 VOR receivers. Most of them have dual VOR. Yeah, not all of them, but most of them. In fact, it's kind of.
So if you have 2.
Yeah.
No, but you said you check them
Against each other.
Does that mean you verify both of them?
Yeah, so what you do is you tune them both into seal beach. You sync them both, right? Press sync or spin until the needles are centered, and you compare what radial they're both pointing to. The difference between the two can be no more than 4 degrees. Difference between the two, no more than 4 degrees.
But it's not plus minus.
It's not plus or minus 4 because you don't know what radial you are, and that's the whole point. You're testing it. So just sync both of them, and if they agree with each other plus or minus 4, you pass.
But like, if you have 2, you can do the other forms, right?
You can still do the other ones. You just have to do them for each.
Each like individually.
Correct.
So most people just do them like cross each other.
Yeah, if I had 2 VORs, I'd probably just do a cross check. Unless I'm at an airport like here, we have the VOT, in which case that's super easy.
Oh, so that's the one that you're on the ground. You just
VOR test signal, exactly. Yeah, 360 from 1802. So how do you keep track of this? Unlike other maintenance logs or inspections, which go in the maintenance log of the aircraft, this one, you just have to do the following. Write down the date, the place, the bearing error, and sign it.
SLED.
SLED is the acronym for this.
There's another one.
What is it?
Does it?
Could be.
That?
Might be.
I don't know. But he looked at me
If
weird
you
when
think of it, like, let us know.
he
Again,
looked
different
at
things for different folks. Like, but SLED, signature, location, error, and date.
Oh, depth.
Oh, P instead of L for
Yeah.
location, place instead of location. That works. That works.
He
Same
looked at me
stuff.
I told him SLED. What?
In our logs, we also include your certificate type. It's not required per 91-171, but what is required per 91-171 is that it be a private pilot. So on our logs, we write down our cert to verify that it wasn't a private pilot who did it, because that would not be legal.
That wasn't a student.
Correct. Sorry, a student pilot. Did I say
Oh,
that?
he
My
said
bad.
right.
It's not a student pilot. My bad. My bad.
Just stay on private, or do you say the certificate number?
No, you don't have to put your number. Just put PPL.
Uh,
COM.
Can't read.
Come on, join me. It's amazing. It's amazing.
So
You'll be there soon enough. You'll be there soon enough. Those are the tests. And I think we actually got, we didn't do DME. We'll do that very briefly and then we'll close. DME is the distance from the VOR if it has DME installed in it. The most important thing is that this also uses time, a time signal, kind of more like the sonar that you were thinking, although it doesn't actually bounce it back, but it's a time-based calculation of our distance. However, DME is a slant range distance, meaning it's literally the straight line between my plane and the DME. So as I get closer, my slant range error is going to be higher than when I'm farther. You look at this example, right? Like when I am directly over the DME, if I'm at 5,000, 6,000 feet, I'm going to still show that I'm 1 nautical mile away, but it's just 1 nautical mile straight up. It's always the slant range distance. So slant range distance is the worst when we are close or when we are Really, it's much more close. I also do with altitude. Yeah. DME is most accurate when the aircraft is further from the nav aid and at lower altitudes. That's because it flattens out this triangle. We do not have DME in our plane. However, we use GPS distance, which is not slant range. It's actual distance across the ground. So our GPS, when we're directly over, it shows distance 0.
That's what I got confused. I took the PPL class.
Yeah.
On Friday, and we
Yeah.
did that exam. And then
Yeah.
they're like, is the DME slant distance or regular distance? I don't know. Oh, it's regular distance.
No, it's slant.
The VOR,
Mm,
the
the-
VOR DME is
Correct. GPS is always just straight up ground distance.
That's right.
However, the FAA says that we can substitute GPS ground distance for slant range DME. The FAA says that's kosher, that's allowed. You can do that. There's going to be a slight difference. We should know that. But it's within enough tolerance error that they're like, okay, fine, you can use GPS.
So, right there for that example,
Mhm.
that's GPS distance. It's 30 nautical miles.
Correct.
That means if it was slant, it would be.
Longer.
It'd be slightly longer. That's this example. It's the hypotenuse of this triangle,
Oh,
right? A squared plus B squared equals C squared. Man, I love it when high school shit comes in handy. Huh? Right?
I'm a
That's yeah. Call your geometry teacher. Be like, I know I told you we'd never use it again. I just want to say we finally used it. Same with the physics teacher. We talked about refraction today. A lot of science today. Yeah. We talked about math today. There's a lot of you got to be smart to be pilot. But anyway, yes, this is going to be longer, right? So this plane, it's not drawn here, but the ground-based distance, if this slant range is 30, that means this is going to be less than 30.
You can actually get that because you get the distance.
Holy moly, you're right, because we're that's right, because we know this is 5,000 and we know this is 30. So we can actually do Pythagorean theorem and figure out exactly what it is. Hell yeah. Jacob's like, no, I'm out. It's enough to know that it's this. Good times, folks. Good times. Now we're getting into some of the meat potatoes of IFR. Tomorrow the charts. Wednesday departures. Thursday weather. That's what plan. AIM chapter 1 is your friend. Anything you want to review? Especially the GPS and the WAS videos from Flight Insight, I do recommend. There's a lot of videos out there. It's a complicated thing, but that's our deal. Thanks for making 7 a.m. so fun. Appreciate you all very much. Is anybody flying today?
I'm flying at 11. Hopefully the weather clears up.
Nice. Thanks for joining Caden and Wayne and Paul. Appreciate it.
Thanks. Have a good day.
You too.
Your mark, we're gonna be dismantling.
They're gradually turning them off. Yeah.
What's gonna be the replacement for like old